Okay, welcome to Lesson 1. This is Section 1.2 in AB Calculus. And the first unit of study in calculus is examining what happens at one location. And to examine what happens at one location, we got to see what is happening on either side of it. And if we're looking on either side of it, it's called finding a limit. Now, to find a limit, we're going to need to look at it graphically or numerically. So today, through this lesson, you will need your book, your calculus book with you, and you need a calculator. We're going to be using the calculator to help us evaluate limits. Again, limits means what happens at specifically one location, looking at what happens on either side of it. Here's the notation for a limit. And we're going to write this out in words. So it means the limit of f of x as x approaches c is equal to L. Now, notice that C is a number, L is a number. So you're looking at a specific C location, which will correspond to your X value, and it's equal to L, which corresponds to a Y value. All right, so let's look at this particular function. F of x equals x cubed minus 1 over x minus 1. Notice that something specific happens right here. We'll talk about it tomorrow in class. Be ready to talk about that particular situation, why that occurs. All right, but we're going to put this into our calculator, so get out your graphing calculator and go to your y equals key. And remember, when you're typing in a fraction, the numerator needs to be in parentheses and the denominator needs to be in parentheses. So open parentheses, x cubed All right, so I typed in my function. Now I got to think about what it's going to look like on my screen. So I want to look at it as the same as on what I have described here already represented on the notes for you. So to do that, I'm going to go to Window, and right now I have it in another form, so I want to kind of have it expressed the same way it is here. Notice that it really doesn't seem to go very wide. It doesn't go from negative 10 to 10. So let's just go from negative 5 to 5 and let our x scale be 1. Our y minimum, it doesn't appear to go below the x-axis, so let's let our y min be 0, our y max 8, and our y scale 1. All right, let's graph that guy. All right, here he comes. We know it's kind of looks like a parabolic shape, even though we know originally the numerator is a degree of 3, so that's a little bit of an interesting analysis. But notice the calculator doesn't put in a necessary piece of information. So this is kind of worrisome. The calculator doesn't quite give us an accurate view. So why don't we see what's really going on around that point 1, where x is 1. We don't really know what's happening at that location. And we're going to look at this numerically. So this is the graphical representation. And we're going to look at this numerically. To do that, we're going to do table on our calculator. So go to the next page. All right, to set up our table, we're going to go use table start, or table set, excuse me. So that's the blue function above the window key. Second window gives me the table set. We're looking at what happens on either side of 1, so let's start at 0.9. And let's increment the table by 0.01. That's a really small increment. We can take our time working our way up to 1. Okay, then I'm going to quit the screen, and I'm going to go second table. And for this function that I have highlighted, is incrementing the x values by 0.01, which we already told it to do, but we're not really concerned about that. We want to see what the y values are doing. So 2.7, 2.73, let's get a little bit closer to 1, 2.9701. It skips 1, so there's an error message. You can tell me why. Write that down in your notes. And then at 1.01, it's at 3.03. So notice both these values on either side of 1 are really close to 3. So as the value of x approaches 1, you have to examine what happens on f of x on either side. All right. So notice on either side of 1, getting closer and closer to 1, our y values are approaching 3. So that we write the limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3. Because the y values on either side of 1 get closer to 3. Notice I didn't care what happened at 1. I wasn't concerned about the value of the function at 1. I was concerned about the values of the function on either side. So notice, to determine the limit of the function, you can examine the values of the function on either side of whatever limit you're trying to determine. You can use a graph, like on page 1 of our notes, or a table of values. You can use table set in your notes or on your calculator, or make your own table of values. All right, let's look at a couple of other categories. And I'm going to be writing down examples from the book, so you want to turn to your book to page 49. Now these are the conditions that these examples in your book will cover. One would be a graph that has a hole, and we just looked at one that had a hole. Hole with x defining the location. Left and right hand values differ. Unbounded behavior isolated. So these are all looking at particular functions that don't follow the normal patterns. They're not graphs of the parent functions necessarily. They have special conditions in them. So we're going to look at either the graph or we're going to look at a table of values. Whichever one seems to be the easiest for us to determine the limits. So we can graph on the calculator, we can sketch our own graph, or we can use table. All right. Well, let's look at example 1. Example 1 is y equals x over the square root of x plus 1 minus 1. So go ahead and look at the denominator. Determine when the denominator is equal to 0. So if x equals 0, notice that gives me a 0 in the denominator, which we know that makes that function undefined. So example 1 wants us to look at the limit as x approaches 0 of 1 over square root of x plus 1 minus 1. Well, since it's not graphed for me on my paper, it is graphed in the textbook. So let's just look at the graph in the textbook. All right. Notice that here's the graph. And at 0, we have a hole because 0 makes the denominator undefined. So coming up from the left side of 0, my y value approaches 2. Coming from the right side of 0, coming back down towards 0, my y value approaches 2. So on either side of 0, my y values are getting closer to 2. Notice that they gave me a table of values. And they increment them pretty close, as much as they can, to get to 0. Coming up from the left side, my y values get closer to 2. Coming down from the right side, coming back towards 0, again, my y values get closer to 2. So the limit as x approaches 0 of 1 over square root of x plus 1 minus 1 is equal to 2. Let's look at the next example. This is example 2 on page 49. We have f of x equals 1 when x is not equal to 2, and 0 when x equals 2. So let's just sketch a quick graph of that. We don't have to look in the book. We can do that ourselves. So when x is not equal to 2, so something happens specifically at 2, and when x is not equal to 2, then the function is equal to 1. So at 2, 1, I'm going to put a hole because it can't equal 2 at that when y is 1. So on either side of the function, I'm going to put a horizontal graph. But if x is equal to 2, then its y value is going to be specifically 0. All right, so this is a piecewise function, and we graph the piecewise. Now the question asks the limit as x approaches 2 of f of x. So coming up from the left side, my y values remain 1, coming up from the left. Coming up from the right side, my y values are 1 again. So the limit as x approaches 2 of this function f of x is going to be 1. Notice I don't care what this value is where it's actually defined. I just know that it's that coming from the left and the right, the y values are 1 and they agree. All right, so that's another important piece of this, is that to determine a limit, the left hand and right hand values must agree. It means they must be the same number. Okay, so let's see what happens when left and right hand limits are not the same. Let's see if something specific happens. Go to example 3 on page 50. All right, so I want to find the limit as x approaches 0 of the absolute value of x over x. Okay, so looking at that graph, we're just going to go ahead and graph this very quickly. We know that x can't be 0, so I'm going to put a 0. I'm going to put a hole in the graph at specific locations when I figure out what's going on. And the numerator always stays a positive. But when the denominator is a negative value, that means the whole thing would be negative, so at 0. And any number over itself is just 1, so all those values are going to be negative 1. And then a positive over positive remains a positive 1. So there's the graph, and you can look on page 50. At the corresponding graph. Okay, we're going to look at that. The limit as x approaches 0. So coming up from the left-hand side, all my y values are negative 1. Coming from the right-hand side back towards 0, my y values are positive 1. The left-hand value and the right-hand value are not the same. They do not agree. Therefore, the limit does not exist. So in order for the limit to exist, the left-hand and right-hand values have to approach the same number. Again, I'm not worried about what happens at 0. I'm worried what happens on coming from the left and from the right. All right, example 4, page 50, is y equals 1 over x squared. So I'm going to sketch a quick graph of that. Got a vertical asymptote at 0. The denominator is always positive. So I've got a nice function that the y values never go below the x-axis. You can follow along with the graph on page 50 also. All right, so I want to know the limit as x goes to 0 of 1 over x squared. All right, so coming up from the left side, notice that the graph continues upward to infinity without bound. It gets bigger and y values get bigger and bigger. So this goes off to positive infinity. From the right side back towards 0, this graph also goes toward positive infinity. But positive infinity is not a value. It's not a number. Therefore, the limit does not exist. But it is allowable to say the limit is positive infinity, meaning that at the point of discontinuity where you have an asymptote, that the branches will both go off to positive infinity. All right, let's look at another special case, example 5. y equals the sine of 1 over x. And let's go back to your notes. Okay, let's go to the calculator and see. Let's practice a little bit with the calculator here. So go to your y equals key. And let's clear out the function that's in there. And let's type in sine 1 divided by x. All right, now before you start using your table, you got to go check to see if your calculator's in radians. All right, so let's check our mode. It is in radian mode. All right, then I can set my table. I'm going to see what happens on either side of 0. So let's start at negative 0.9 and increment by 0.01. And let's look at our table. So looking at our table, negative 0.9, I've got negative, negative going toward. I think I must have entered a negative. Let me go back and see what I entered. Oh, negative 0.76. So let's start at negative 0.9 and go back to my table. Here we go. All right, so I've got negative values. And I'm getting closer and closer to 0. But notice what's happening to my y values. They're not really following a specific pattern. They go to negative 1, and all of a sudden my y values pop over to a positive, going toward 0. All right, I'm getting closer to 0. And I'll pop back over to a negative value. And now it pops back to a positive value. And at 0, I have an error function. So on one side it's a positive value. On the other side it's a negative value. Let's look at this graph. So graph this function. Probably need to go back and reset my screen, obviously. So let's go to Window. And I'm going to go from negative pi to pi. My scale is 0.1. And let's go from negative 5 to 5. Or excuse me, negative 2 to 2. Now, why do I need to only set my screen to negative 2 and 2? Be ready to answer that tomorrow during class. In fact, I could have gone a little bit smaller than that, but I'm going to set it from negative 2 to 2. Graph, here it comes. Now you can see that graph jumping. This is called an oscillating function. And when a graph oscillates on either side of one location, then the limit does not exist. It doesn't have the same value consistently coming from the left or from the right. All right, so tomorrow during class, we're going to work on page 54. And some of these are going to be used for the calculator. Be ready to talk about these notes in the morning. Plus, we're going to talk about an easier way to find these particular values in your calculator. And part of it's going to involve using a couple of new keystrokes you may not know. And we won't use the graph. We're going to use another particular valuable key in your calculator. Let's go to number 11, for example. Let's look at that limit for a second really quickly. When we're coming toward 2, the limit approaches 2 from the left and 2 from the right. So the limit of this function is 2 as x approaches 2, not 0. So be ready to go over this and